Good afternoon. Welcome to the Tutte Colloquium. I'm happy to introduce Kostya Pashkovich. I think most people know as a professor here in our department, to talk about Matroids today. Please, the floor is yours.
Thanks a lot for the introduction, and thank you for coming today. Hope you don't regret it on the long weekend. And this is a joint work with Sina Kanstantsin, and it's going to be about results that was known for some time. It's one-half approximation for Matroid profit inequality. What's new here is that we claim that our algorithm is substantially, it's simple and almost non-adaptive. So I will just explain what does it mean. But before going there, I would like to just define the problem. And I will skip the usual massaging of the problem and immediately jump into Bernoulli instances. So those will be the ones on which we are concentrating. So what do we have? We have elements, U, which we consider accepting or rejecting. But it's not going to be so simple because we'll have a matroid on those elements. So you can imagine any kind of like matroid that you like. In case it's the first time you hear, you can imagine that U has a set of vectors in some dimension. And M corresponds to independent vectors that are linearly independent. Okay, so for each element in U, we have a distribution of its value. And those values are independent from each other. We have a value of element E will be some fixed positive number VE with probability XE, and will be 0 otherwise. So elements independently from each other get some positive value VE or 0. If they get if they happen to get this value V, we call the element active. Because the element is active. It's not kind of like important, but if it's 0, it's kind of like useless element. But if it's okay. So what will happen now? We will see the elements in some order. Elements of U will be flashed in front of us in some order. The order will be usually, you can imagine, adversarial. So it's the worst for us order. And each time we see an element, we see its value. And we have to immediately decide whether to accept it or reject it. So at each step, so the elements are shown to us in some order, and when the element E is shown, we see the value of E, what is really is realized. We see them in some order, and each time we have to immediately, so as soon as we see the value of the element, we have to immediately, so the issue is that we have to immediately and irrevocably, so this is quite intimidating part, decide whether to accept, reject E. And we would like to maximize the value of all elements that we accept. So as you can imagine, we cannot just accept all the elements. The issue will be that at each time point, we have to be independent with respect to Matroid M. So if it would not be the case, we would be accepting all elements. But we cannot do that because we have to keep independence. So the set of accepted elements should be always should be independent in the Matroid M. So that's okay. I mean, like, there are several catches, but okay. Is the problem okay? Okay. Yes.
Is there something you're trying to optimize?
You want to maximize the expected total value of elements that you accept. So you from each element that you accept, you get its value, and you want as expected value of accepted set to be maximized. Okay. So one thing that is not really important for now, but it will be important time from time, it's interesting Bernoulli instances. So really we can massage this problem further. So we can massage this problem even further because it's enough to solve, like you can show that it's enough to solve this problem. We can additionally assume that the probability x lie in the Matroid polytope. So what does it mean? That if you consider set S and some x values inside the set, it's going to be smaller or equal than rank. I will omit M here. I will write it first time, but when it's clear from the context, I will omit for every. So you can assume that further the issue is that we will have recursive algorithm, and recursive algorithm will destroy interestingness in the first round. So we will not be operating only on interesting instances, but time from time, when everything is ready and in place, we will kind of like say, oh, just recall, we care only about interesting instances. But really, by default, we will not be assuming that, because it will be destroyed by our algorithm almost immediately. Okay, I said that this result was known for some time, and this is several authors showed it, Kleinberg, Weinberg. Then there was also Lee, Singler. There are other, especially partial cases, which also show the same result. And on Matroid, they essentially provide the same algorithm. On Matroid, they provide essentially the same algorithm. So what do they show? So they show that you can compete with a profit. So what does it mean? So there is an algorithm that achieves in expectation at least 1/2 expected profit gain. So profit, so you can imagine in this case, the element are shown to us one by one. And when we see the element, we do not know the values of the future elements. But profit knows the values of all elements from the get-go. So what will profit accept, essentially? The profit will always accept, essentially, maximum weight independent set in the metric. So maximally over A is independent in M. Sum E in A, value of E. So the problem is that we do not know the value of the future elements, but the profit knows the value of all elements, yes? We know everything we know except value. So everything that stands on this board we know except the values, because values correspond to the real random variables. They will be shown to us one by one, their realization.
We even know the meter structure.
Sorry?
We know the meter structure.
Yeah, we know, let me maybe even highlight what do we know. We know U, we know M, we know VE, and we know XE. All of that we know from advance. Okay. So it's a bit tough benchmark to compete with. It's kind of like someone who has information that you don't have and have no opportunity even to get. Because this profit knows all future arrivals even before it happened. And let us see why this actually is the best possible. So I will just do one example to make sure that we are on the same page. Because last time I was accused that I did not explain the problem well. I tried to explain. So let me be sure that. Okay, so I will have two elements, E1, E2. And M will be very simple. M essentially saying you can accept at most one element. So M is one uniform Matroid. Okay, on U. So what is the value? What is the value of the first element? So the value of the first element will be parameterized by epsilon. The epsilon is quite small. So with probability epsilon, it gets 1 over epsilon. So it has very huge value with probability epsilon. So epsilon, you can imagine, very small. And it gets 0 otherwise. The value of E2 is going to be always 1. The value of E2 would be always 1. So let us see what the profit gets. The profit gain, so because profit knows all values from get-go, so the profit will always know when this element has high value. And this will happen with probability epsilon, and the profit will be able to catch this 1 over epsilon immediately. With probability 1 minus epsilon, the profit will not be so lucky, but it will be able to get 1. If we open that all together, it's going to be 2 minus epsilon. But now you can imagine what would be the adversarial order in which we will see that. We will not see that in the order E1, E2. The adversarial order will be to show us first the value of E2, and we will learn nothing, because E2 has value 1. And then we will be forced to irrevocably and immediately decide whether we accept it or not. If we accept it, we get 1. If we reject it and wait for E2, in expectation, we get again 1. So any algorithm, so one cannot in expectation get more than 1. You can formally show it. Because if the order is adversarial, you will not be able to see. And you can see that this gives you exactly the idea why one cannot push this 1/2 any lower. Even for the most simple algorithm, you cannot get this constant larger than 1 over 2. Okay. So it looks like it's all done and settled. So let me describe the results that we got, because we wanted to return to this problem, but we wanted the algorithm that was of very specific structure. So this theorem and this algorithm requires a lot of computations that should be done on the fly. You have to compute, recompute certain values through the whole algorithm. But we wanted it to be non-adaptive, essentially. We wanted all computations to be done from the start, and then it's kind of like runs by itself. It was crucial for us because otherwise it was hard for us to deal and plug this algorithm any further. So what do we show? Okay, so our algorithm will be non-adaptive, but we will have to change the matroid a bit. We will have to make it stricter. Because you see the matroid M imposes on us some constraints. We will be even more strict on ourselves. We will impose even stricter constraints. So we will change the matroid to another matroid. There is a matroid M prime. There are many ways how I can kind of like write what I want to say. The idea is that every set that is independent in M prime should be dependent in M. So the constraints are stricter. Everything that is independent in M prime should be independent in M. So let me just write it for the sake of space. I will just write it in a different way, such that I will write that the rank function is dominated from above. Rank M prime of S is smaller or equal than rank M of S for every S in U. So that's how I will write it. But essentially, the matroid M prime is stricter. Everything that is independent in M prime is independent in M. And we will be trying to work only with M prime. We are strict on ourselves. And there are thresholds. There are that we can fix from the start. So for each element, we can fix the thresholds from the start. Okay, I will erase maybe this. So we will be running the most simple algorithm. We will be accepting elements greedily. If the elements comes and its value is higher than the threshold, and it's feasible for us to accept it with respect to matroid M prime, we will accept it. So that's what we are planning to do. Like we are planning to really not even bother. We will be accepting them greedily, such that the algorithm that accepts every E in U whenever its value passes a threshold, value of E passes the threshold of E. And it's possible to, that accepts every E whenever value. And it is feasible to accept, because it might be that the matroid M prime stops us, it's feasible to accept E with respect to M prime. Such a simple algorithm, it is kind of like almost non-adaptive, achieves an expectation at least 1/2 of profit gain. And to the best of our knowledge, this is the first algorithm that is different from the structure of the Kleinberg and Weinberg and Lee and Singler that follow essentially the same computations throughout. Yeah.
So then we had the base, but I don't understand how the value from being greater than 0 will be sub 8.
Sorry?
Value
Yeah.
has to be either 0
Yeah.
So this threshold,
So if the threshold, for example, is above VE, then the element is never accepted. If the threshold is between 0 and VE,
is this TE independent, like given by the matroid, and independent of the values?
TE is, this is function of Matroid, X, and small v's. So because value of E is distributed as Bernoulli, it's VE with probability XE. And it's 0 otherwise. So value of E, sorry, I just erased it. So it was VE with probability XE, 0 otherwise. So the threshold of the element, and also E itself. So the threshold is depending on the matroid, on vector X, on vector V, small v, and
But the value you take to at 0 or
yeah.
I can see why you're not saying take it if it's positive.
Sure, you can, sure, I mean, like, it will be depending on the threshold. If the threshold is above small v, VE, the element will always be ignored. If the threshold is between, so you have kind of like,
There's like two values of TE that you sort of are choosing between. Something lower than V and something above V.
yeah, so I mean, like, there is case when, so I have here 0 and here VE. If my TE is between them, I'm accepting the element whenever it has positive value. But it also can happen that my TE is kind of like above VE, really. So in this case, I never accept the element. So it's kind of like, in this case, I will never accept the element. It simply allows me to push two cases in one statement. Yeah.
Does this hold much the same for arbitrary distributions, like non-Bernoulli?
Yeah. This whole kind of like Bernoulli thing, it's massaging. I skipped the massaging. This is kind of like the most, the kind of like the hardcore instance. After you did all massaging of any instance, you will get Bernoulli.
And you see each element of the universe just once?
Yeah, just once. Just once. Is there any questions?
So just to follow up, so at least in this like Bernoulli case with this, instead of choosing TE, you could have just chosen a subset of the edges. And if you're outside that subset, you'll never accept. And if you're inside it, you accept if you see the positive value.
For example, yeah. You can do that. You could reformulate it this way. I had to optimize for the sake of the board. It's all the formulations are good and valid. I just had some specific objective function in mind. Okay. Okay. So just to be clear, why do we say almost non-adaptive? Almost non-adaptive comes from the fact that we are changing the matrix. We are changing M to M prime. This is why we are speaking almost non-adaptive. There are results that are showing that if you don't change the matrix, you cannot achieve any constant approximation. You cannot achieve even log of number of elements as approximation. So if you plan to keep static thresholds and do not change the matrix, you are really not constant approximation. But since we have to change the matrix. And because of this change, we call it it's almost non-adaptive. But really, we are not doing any adaptivity after that. Yeah?
One usually uses the term adaptive to mean that you make a decision after you see the elements that are presented to you. But here it looks like you can compute M prime before you see any element.
Yeah, so this is not our religion. I mean, like, this is essentially the testament that we got from the people who coined that, and we are operating with it there. They had like different idea in mind because they wanted to kind of like have some reductions from different problem to this problem, and they started to distinguish that, whether one changes the method or not. But technically, you're right. For me, it would be non-adaptive. But since I'm kind of like coming to a different temple, I'm absorbing the terminology. Any other? Yes?
Sorry, one last question. So then the profit gain for n prime becomes greater, or sorry, becomes less.
Becomes less. Yeah, but you are still getting profit gain in the, this is profit gain in the old matrix in M. So you essentially change the matrix, you're competing in stricter condition, but you are still achieving profit gain in M. So this is the whole point for us, because otherwise you could change to the matrix where everything is loop, and then profit can get only 0. So we cannot do that. We have to compete with the previous benchmark. Thank you, that's an excellent question. So we are strict on ourselves, but our benchmark is not relaxed. Okay, are we still on the same page? Okay. Okay, so let me just define the threshold that Sina came up with, and that was actually the key part of the whole thing. So let us imagine we are making a wild guess. So let us say we don't want to have even threshold different by the elements. So we first can try to see what happens if we impose the following threshold. And this is going to be a threshold with which we are kind of like trying to work as much as possible. So definition, so if I have a Bernoulli instance, so let MXV be a Bernoulli instance, then for each set we can come up with some function for S in U. We define threshold of S. This is essentially, first of all, above will stand expectation if you would have not even matroid constraint, if you could have accepted everything that comes your way. So this you would get. If you would be accepting every element that you want, this would be your expected gain from S. And it's going to be divided by rank of S plus summation. So here, sorry, so here we assume S is non-empty, so that we don't have division by 0, and XE is bigger than 0 for every E. It's kind of this assumption. None of the assumption is particularly restrictive. If element is always having value 0, just ignore that element. So and S is not equal to 0, it's simply that we remove. Okay, and here comes the first baby version of this theorem that Okay, just maybe let me just spend a couple of words. So for some specific cases, for uniform matroids, this kind of like function was kind of like appearing here and there, but usually it was rank of S plus rank of S, so twice rank of S. So, and Sina noticed that actually analysis is working out in many cases if we just have here total mass of X on the S, and we can save a lot of things, and the formulas are working out, because with 2 ranks, the formulas are not working out. And 2 ranks are usually appearing in many specific cases. And here the key whole point was changing the function of the threshold. Okay, so what was the baby version? So from where, from where does this function at all comes? So the baby version is essentially saying that if we have a Bernoulli instance, and it happens that the global threshold, so what is the global threshold? The global threshold, if you plug the whole ground set inside, is dominating every other threshold. So Ts for every S in U, S non-empty. Yeah. Then we can just run the algorithm with the same matroid M and this single threshold on every element. Consider that accepts every element E whenever it passes a threshold. And it's feasible to accept it. We don't even need to change the matroid. Then this algorithm achieves in expectation at least, okay, and here comes a bit strange expression, T times rank of U. So essentially T times rank of the whole matroid. It looks a bit strange at the moment, but let me return to the interesting instances. So for interesting instances, T times rank U, this is, I will just first simply rewrite what is T means. T means summation of VEXE, E in U, divided by rank U plus summation of all x's. times rank of U. But because the instance is interesting, we can bound this thing by rank of U as well. We can bound it by the rank of U as well. So we will have twice rank of U times rank of U. So it's going to be bigger or equal than 1/2, because we lose here 2 ranks times rank, 2 rank summation E in U, VEXE. But summation of VEXE, like, it's essentially expectation of the total gain of all elements, even without the Matroid. So this is clearly going to be, so this is if you allow to accept every single element that you see, that's what you get. And this is clearly will dominate profit gain. So for the nice, so for those nice instances, whenever they're interesting, we get our theorem. So if it happens that the threshold computed at the whole set U dominates thresholds of every subset, we can get for the instances where we are really interested, we can get 1/2 approximation. Yeah.
So you have one threshold for every element?
Yeah. But this is only for this specific case. Global threshold dominates every threshold on subsets. It's only for those things. So essentially, like when you have more restrictive constraints, it might be that your most valuable elements are hidden somewhere inside. So this is kind of like saying, actually, all elements are kind of like on the global level. It's kind of like the idea, and so you can run with a single threshold and accept them. Okay. So that's, let me show the proof of this theorem, because what I want to convince that the proof is easy. It's easy. I don't know whether I will manage to do that, but I hope I will. So, yeah. So removing those things. Okay. And it might be fun if you did not see the proofs of those profit inequalities before. So, so we're going to prove this theorem. The theorem that goes from 10 to 11. So we are running very clear algorithm. The elements will be coming to us in adversarial order, but the algorithm is quite clear. If the value of the element passes the threshold and we can accept it, with respect to m, we accept it. So we need hold on the random variables that indicates for us a set of accepted elements. Of accepted elements. This is a random variable. This depends on what values really are. And also an adversarial order, on our decisions, on everything, really. But our decisions are more or less fixed. Elements by our algorithm. But so we will need also to hold, to get a handle on the elements that could not have been accepted by our algorithm because they were potentially not respecting Matroid constraint. And for that, we will consider the closure of those elements. So let f be the closure in M of those elements. So element was blocked by Matroid constraint only if it belongs to F, because to be blocked from accepting by Matroid constraint, it should be spanned by the accepted elements. And that will be crucial for us. So if you're imagining linear Matroid, I will be the vectors that you accepted, and closure of I will correspond to the vectors lying in the linear space of vectors that you accepted. Okay, then let us do the gain of the algorithm. Give me gain, algorithm gain. Okay, so, and here comes the first step. It's usually always the same. So, one first, one first accounts for the gains from the threshold, because we accept all the elements that are passing the threshold. So each element that we accept, it will be passing the threshold. So it's T times summation E in I times 1. So from each of that, we will get the threshold at least. But then potentially we also get something on top of that. Some elements will have something on top of that. So it's going to be summation of E in I. All of them passed the threshold, so what do we get on top of that? T. Yeah, T. I hope I'm correct. So we're essentially rewriting the total gain as a gain of the threshold and the gain that was done on top of the thresholds. Okay, so now it's going to be bigger or equal. So the first one is clearly T times expected size of the number of accepted elements. And the second we can also rewrite as the following statement, that we go through all elements in U that potentially could have passed the threshold, because elements that could not pass the threshold are not very interesting to us. They would not be accepted. The gain above the threshold times the probability that they achieved this positive value times the probability that E could be accepted with respect to M when it arrived. So we can rewrite it like that. So we essentially go through all the elements one by one that could potentially pass the threshold. For each of them, we kind of like they're passing threshold only with probability xe, and this probability is independent from probability that previous elements don't violate it. And each time both those independent events happen, we get VE minus T. But this is a bit too much for us to digest. So, like probability that E was not, so probability that E can be accepted when it arrived, it's larger that, okay, the later the element E comes, the later the element E comes, the smaller is this probability. The later the element E comes, the smaller, because we potentially accept more. So what we can essentially say is that we can lower bound that by the probability that E could be accepted after everything is done and we see E again. So let us imagine we saw all the elements and then we see E again. So in this case, the probability that E can still be accepted is the probability that E is not spanned. So it's essentially the later you see E, the less is this probability. So E does not belong to F. So it's going to be when you can lower bound this probability by essentially seeing all the elements and then seeing E again once again. So, and E will be able to be accepted only if it's not enough. And this is clearly 1 minus probability E in F. Okay, so this is, the first term is simply expected. I put T inside, and cardinality of E, because E is independent, is nothing that rank of F. Is nothing that rank of F. And the second term is essentially summation E in U, VE bigger equals than T, VE minus T, XE, 1 minus probability E in F. Okay, if you regroup it all together and put everything that is related to F to one side and everything else to the other side, you will get the rewriting that essentially saying that it's summation VE bigger equals than T, VE this is just regrouping, there is no estimation here, plus expected T times rank of F minus summation E in F VE bigger or equals than T VE minus T XE. So if you just regroup all the elements, that's what you would get. That's what you would get. No, I'm not going to it's simply regrouping them here and there. Like this one will give you the first term, and everything that else is packed in F. And then we will use the fact that the T is dominating threshold for every set. So here, okay. We use the fact that T is, like this was the instance where T was dominating threshold of every set. So T was dominating in particular the threshold computing on F. And this, if you kind of like rewrite it several times, you will get that T times, it's really just equivalent rewriting. It's T rank F minus summation E in F VE bigger equals than T VE minus T XE is bigger or equal than summation VE minus T XE. Sorry, I will just finish the proof of this thing. So this will be just this rewriting. So this rewriting will allow us to estimate that this is smaller, because in each of those expectations, we can essentially just estimate that by this term. So we will get U VE bigger equals than T, VE minus T XE. And then for this thing, we will estimate it like that. E in expectation E in F, VE smaller equals than T, VE minus T XE. And you can see that all of the numbers here are negative because VEs are below T. So you can essentially even, you will decrease this side if you change to larger set. If you include, because all the numbers here, this is non-negative, but this is negative. So the more you will be summing out. But then once you increase, randomness completely disappears. And so what you will see is going to be just the summation of E in U, and then it's the same kind of like thing, VE minus T times XE. Essentially, by definition of threshold, you can see that this is equal to T times rank U. I will not be showing this step, but this is rewriting of the definition of the threshold. This is just definition of T as T of U. So once you rewrite this thing, you will get that those expressions are exactly equal. And this proves our theorem that says that for nice instances where a global threshold is the largest among all, we get at least T times rank U. Yeah, sorry, I was thinking that it's much simpler than it was. So just to be clear, what is going to be, I will not have one page for the whole algorithm now. It's not kind of like, don't think that it's too much left, one page. So just to make clear like how algorithm works. It's essentially, because like we are really interested in interesting instances. We are really interested in interesting instances. And if it happens that in interesting instance, the global threshold dominates all the thresholds, we are done. So what we are going to do, we are going to check whether global threshold is dominating all the thresholds. If it does not happen, if it happens, we are lucky. If it doesn't happen, we select the maximum threshold among all sets and simply extract it outside of the Matroid and put it aside. And on the remaining part, we contract the set that we extracted and repeat the game. We see, is now the instance satisfies that global threshold is the largest possible? If kind of like yes, we will finish. If not, we again select the maximum threshold, extract it and put aside and contract it, and so on. And we can show that this leads us to a direct sum of several matrices that will define for us M prime. And for each of those matrices, we will define the threshold according to the lemma that you just saw. It's going to be the global threshold of the small part. And that will give us 1/2 approximation for small instances. And just maybe one sentence about how we use LLM. I just have like really 1 minute. So what it was helpful for us, On one side, it allowed us to test a lot of hypotheses very fast because we were trying to develop the algorithm and we didn't know like which thresholds will be good, which kind of like extraction procedures will be good, how to select the set to extract, and it was very efficient to test it with LLM. And then once we kind of like started to work on it, we were working particularly on laminar matroids and on laminar matroids of very small level, like 3-level, 2-level laminar matroids. And there, it was very helpful to give us ideas how to organize the proof. Once we had the right thresholds, it was helping us the ideas how to organize the proof, because otherwise it would be very hard, because those extraction procedures are creating a lot of matroids, but then you have to put them all together. And what properties do you need to prove to be able to put them together? It helped us on the small 3-level, 2-level laminar matroids to see what properties do we get. Thank you for your patience. Sorry for holding you so long.
Thank you, Kostya. Are there any questions? Please wait for the microphone.
Is it a polynomial time algorithm?
Oh yeah, sorry, I forgot to say, everything can be done polynomial time. Actually, unlike the previous algorithm, I don't know whether one should brag too much about it, but once you polish it to Bernoulli instance, all the computations can be done in polynomial time. And that's not true for the previous algorithm. They can you can achieve kind of like f-pitas for the numbers that they need in the previous algorithm, but you cannot compute them exactly. Here we compute all thresholds, all matroids, everything, polynomial.
Which LM did you use?
It was ChatGPT. I hope it's not advertisement. Okay.
I have a question which is following up from the kind of middle section of questions. I'm still not clear on what is non-adaptive, because you can construct M prime purely from a description of the original matroid and the values. So once you construct that, then you have a bunch of thresholds that you just kind of look up in memory each time. Am I understanding that all correctly?
Yeah, yeah, that's how I would also understand it. I completely agree. I would call this algorithm non-adaptive. But what kind of like the previous people are saying, like, I will not be mentioning the application, but they're saying because you're changing matroid M to M prime, so that's what they're writing. Because you're changing matroid M to M prime, really you still have your matroid M. And the problem is that now you start to accept elements, and some elements you cannot accept not because of M, but because of M prime. So your threshold is jumping to plus infinity. So it's true that all computation are done before anything happens. But they're saying really for all the reductions, we need to work with the original matroid M. And if you change the matroid M prime, your thresholds at some point are jumping from the original to plus infinity because you so that's, and they need it for reductions when there are essentially several items belong to the same person, and they have it for very specific combinatorial mechanism design problem, why they don't want this property, the threshold jump.
Great, thanks.
I have a couple of questions. So one is because I'm not familiar with this literature, but let's take a non-trivial matroid, let's say a spanning tree matroid, right? So could you, at a very hand-waving level, contrast the adaptive half approximation with your algorithm? How would they operate? What is the contrast? And my second question is a more silly question. That suppose you didn't use any LLM for your proof, would it just have been a matter of more time, or was there some qualitative thing that the LLM gave you?
Okay, let me just go to the second question first. I think like I included LLM only in the absolute because Sina was excited about that really, but to my feeling is that Sina was really the main contributor of ideas here. Like LLM helped to keep us on, like to give us longer breaths. I don't know how does one say it so in English. To kind of like to keep us running, because essentially you need to test a lot of things fast. If you kind of like get stuck for a very long time, it's quite frustrating. So I feel like LLM in this particular case was helping with that, not really with, and maybe of polishing some properties that we needed to show, but not really generating critical ideas. Testing and polishing something. For the graphic Matroid, maybe I have to think more because I don't want to say immediately, because it's a bit hard computation, like when you divide by the... So I can tell you what happens in the adaptive case. In the adaptive case, you essentially, each time you see an element, you do the computation, what is your expected what is expected profit gain if you accept the element, and what is expected profit gain if you don't accept the element, given that you already accepted your previous elements. And then you divide the difference by 2. If the value is above that, then you accept. If it's not, you reject. So this is kind of like how the algorithm is working. How to really... I need to take pen and paper to kind of like reply it in a meaningful way. What does really change? But this is it's very hard problem to really to solve. Like this expected of the profit gain, it's not completely clear how to solve. For some problems like laminar matroids, you can solve that efficiently, for example. But for graphic matroids, I think it's p-space hard. Like it's like some.
Any other questions? All right, let's thank Kostya again.
Thank you.